So if you haven't picked it up by now, physics has a lot of math in it. And in math, there's a lot of ways to make easy, small mistakes, but there's also ways to check your answers. And one logical way to check your answers is called checking the order of magnitude. Essentially, it's looking at the number that you get and asking yourself, is this an approximate value that I could expect when solving this type of problem? So order of magnitude is essentially approximations of values. And what I'm going to do in this video is I'm going to give you numbers so that you can start to get a gauge on some approximate values in the universe. Maybe making sure your number is within a certain range that's reasonable. Is my number way too big? Is my number way too small? It's sort of a partial guess that you can use to make sure that your answers are correct. So the first approximation that I want to give you is the distance from the Earth to the nearest star, which is the Proxima Centauri. I guess that's how you say it. So this distance is very, very large. Anytime you're dealing with distances in the universe or solar systems, you're talking about very large distances. And by the way, this is Earth's nearest star, not counting the sun. We'll get into that distance in a little bit. But you can see that from the Earth to Proxima Centauri, it is about 40 quadrillion meters. And to give you sort of an order of magnitude, it's probably easier to use scientific notation, which this is an order of magnitude of times 10 to the 16th. And this is one of those examples why we like to use scientific notation for these really big numbers. But if you were to put that in kilometers, it's 40 trillion kilometers, which is an order of magnitude of times 10 to the 13th. And just so you can see, that's 4.24 light years away, which means it takes light from Proxima Centauri 4.24 years to reach Earth. Now, just to show you a drawing here, we have a little bit of a diagram showing how far away Proxima Centauri is, and in reality, this picture isn't even to scale. It's just showing that it's well beyond our solar system. But this diagram does show some order of magnitude because it says if from the sun to the Earth, if that's considered 1, and we call that 1 AU or astronomical unit, which is the distance from the sun to the Earth, Proxima Centauri is somewhere around times 10 to the 5th or 10 to the 6th astronomical units. So the order of magnitude using AUs is somewhere around that range of 10 to the 5 or 10 to the 6 AUs, which is extremely far, but it is the second closest star to the Earth. Let's talk about something else. Let's talk about how far does light travel in a year. So we know that a light year is the distance light travels in 1 year. Well, light travels about 9 quadrillion meters in a year. And that's an order of magnitude of about times 10 to the 15th. And if you were to talk about it in kilometers, 9 trillion kilometers. So trillions are usually somewhere around times 10 to the 12th when it comes to order of magnitude. And just a fun little fact for you, it takes light to travel from the sun to the Earth somewhere around 8.5 minutes. So if the sun were to suddenly stop working, don't worry, it's not going to do that. But if it were to suddenly stop working, it would take us about 8.5 minutes to know it. Anyway, moving on, let's talk about the average distance between the Earth and the sun. Well, the Earth and the sun, they're about 210 billion meters away from each other. So the order of magnitude of that is somewhere around times 10 to the 11th. And if it was in kilometers, it'd be somewhere around times 10 to the 8th. So you notice order of magnitude is not an exact answer. It's more of an approximation to get the range of which the answer is going to fall in. So we talked about the distance from the Earth to the sun. Let's talk about the distance from the Earth to the moon. Well, the Earth and moon are somewhere around 400 million meters away from each other, or 400,000 kilometers. So 400 million is around the order of magnitude of times 10 to the 8th. And 400,000 is somewhere around the magnitude of times 10 to the 5th. Now, what about satellites and their altitude above the Earth? Like, how far above the Earth's surface are satellites? Well, somewhere around 200,000 meters or 200 kilometers. So the order of magnitude of the 200,000 is somewhere around times 10 to the 5th meters, and then the 200 kilometers is somewhere around times 10 to the 2nd. So we're starting to get closer and closer to the Earth. We're getting to smaller and smaller orders of magnitude. So what about something like a football field? Well, football field is relatively small compared to all the numbers that we've been dealing with. A football field is around 90 meters, or if you're in America, 100 yards, or 120 yards if you're counting the end zone. Anyway, that's an order of magnitude of times 10 to the 1st. or just times 10. So let's keep going smaller and smaller. Let's talk about the length of a horsefly. So a horsefly is about 0.005 meters or 5 millimeters. And because we're talking about really small numbers now, our scientific notation is going to be times 10 to the negative something. So this order of magnitude is somewhere around times 10 to the negative third meters. So if you're talking about something around the size of a horsefly, you know, this is sort of the range you're looking for. If for some reason we're trying to solve for the length of a horsefly and you get something with a times 10 to the 15th power, then you know something seriously wrong happened. So this is just a way to check and make sure your answers are correct. So let's talk about a dust particle, something really small. Dust particles are about 0.0001 meters or 0.1 millimeters. And the order of magnitude of that is times 10 to the negative 4, and that'd be meters as well. So let's keep going smaller. Let's talk about the typical size of a cell. Now, a cell is about 100 micrometers, and we could, count the decimal points backwards, 1, 2, 3, 4, 5. So that's an order of magnitude of times 10 to the negative 5th. And let's go even smaller than a cell. Let's talk about the diameter of the hydrogen atom. So it's about 0.1 nanometers. And if we wanted to, we can count the decimals here as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about times 10 to the negative 10 meters. That's around your order of magnitude, what you would expect if we're talking about the diameter of a hydrogen atom. Extremely small, very, very small. So those are all approximations of length, but we could also do approximations of mass values as well. So if we're talking about the mass of the sun, you could see that that's a really, really large number right here, this mass of the sun. So let's see what the order of magnitude of this is. And I'm not going to count the zeros out for you on this. I've already done it for you, and I'm not going to bore you by making a whole video about me counting zeros. But the mass of the sun, which is a very, very large mass, is of the order of magnitude of times 10 to the 30. So it's very, very big. And then if we're going to go down to the Earth, it's around the order of magnitude of times 10 to the 24th. And then the moon is somewhere around times 10 to the 22nd. And we know that the sun is larger than the Earth and the Earth is larger than the moon. But now let's go down to something that is man-made, a very, very large man-made structure, which is the Golden Gate Bridge. So it's about 805 million kilograms. And that's an order of magnitude of somewhere around times 10 to the 8th. If we're going to go down to a pretty decently sized shark, they're about 100 kilograms. So that's around the order of magnitude of times 10 to the 2nd. An average human, somewhere around 70 kilograms. So that's somewhere around times 10 to the 1st power for your order of magnitude. A frog of 0.1, so that's times 10 to the negative 1. And then if we're talking about the mass of a mosquito, that's somewhere around times 10 to the negative 5. And if we go even smaller to a bacterium, that's around times 10 to the negative 15. You can see all the zeros that come before it. Now, what about the mass of a hydrogen atom? It's extremely small mass. And the order of magnitude of that is times 10 to the negative 27. So you can kind of see that it's very, very, very tiny. And even going down smaller, down to the electron, it's somewhere around times 10 to the negative 31. So now you can kind of see an order of magnitude of all the different masses. And it's good to see this because if you're trying to get the mass of a car, you would think it would fall somewhere between the Golden Gate Bridge and a shark. So maybe the order of magnitude of a car would be times 10 to the 3rd or times 10 to the 4th. But you would not want the mass of your car to be somewhere around times 10 to the 22nd because no car is actually that massive. And it's also not so small that you would get something like this, like times 10 to the negative 1 or 10 to the negative 5. Anyway, let's go on to the next one, some approximate values of time. So the average age of a college student is a lot of seconds. We usually don't measure it in seconds. We'll say years or something, but it's that many seconds on average. And that's an order of magnitude of times 10 to the 18 seconds. And just 1 year, if we're measuring it by seconds, is times 10 to the 7th. And then 1 day, which is somewhere around 90,000 seconds. It's actually 86,400 seconds. But remember, we're doing approximations here. So it's about times 10 to the 4th. That's the order of magnitude of seconds in a day. Now, if we're going to go shorter to times between heartbeats, that's 0.8 seconds on average for most people. So that's an order of magnitude of times 10 to the negative 1. In the period of a radio wave, maybe you don't know this, but the period of a radio wave is the time it takes for one radio wave to go past you. And it's a very quick time, as you can see. It's an order of magnitude of times 10 to the -6. And that's because radio waves move extremely fast. And then a very, very short time period, the duration of a nuclear collision. As you can see, it is a very, very, very short time, order of magnitude of times 10 to the -22 seconds. Now at this point, we're getting really, really close to being able to just jump in and start solving some physics problems and learning a lot about physics. But there's two more things I want to teach you if you watched all my previous videos. If you haven't watched my previous videos, you should go back and watch them. But in the next video, I want to show you all the different trigonometry that you're going to need to know before you dive into physics. And you might already know some of it, so it's going to be a really quick review.